Let's start a discussion about isotopes. So the prefix iso in chemistry is pretty common. That prefix means the same. For isotopes, we're looking at atoms that have the same number of protons, but different numbers of neutrons. Since they have the same number of protons, they're all going to be the exact same element because the number of protons is equal to the atomic number, and that gives the atom its identity. So think protons equal identity. Protons plus neutrons, all those are the nucleons located in the nucleus. That tells us the mass of a particular atom. So isotopes have same number of protons, different number of neutrons, and as a result of the different numbers of neutrons, they're going to have different masses, even though they're the same exact element. So building off of that idea, let's look at an example. Here we have 3 isotopes of carbon. There is an error. I don't make my own images, so I copied this off of Google at some point. It does a great job showing what's going on in the nucleus. However, there is a little mistake in one of the drawings. So you'll notice that carbon 13 and carbon 14 both have 6 electrons around that nucleus. But for some reason, the first image, they left off an electron. So I just drew in an extra electron. And you can do the same, and you can put that electron wherever you want in that second shell. So since this has 6 protons and 6 neutrons, we know that its mass equals 12. And one way that we can designate that, probably the easiest way if you're typing something, is to write carbon-12. And that tells the person reading what you wrote that you're thinking about the carbon-12 isotope specifically. 6 plus 7, this gives us a mass of 13. And 6 plus 8 gives us a mass of 14. But again, each one of these is carbon because the number of protons remains constant. Looking at our periodic table, we see that carbon has a mass of 12 AMUs. And honestly, at some point, you're going to just know that off the top of your head because carbon is so prevalent in so many different molecules. What does that mean, though, in terms of the isotopes? All of the isotopes exist naturally, but when we look at the periodic table, that value represents an average of everything that's going on in nature. And we're going to learn how to calculate those averages. So since on the table, it kind of looks like carbon-12 is it, that tells you that most of the carbon that we're going to encounter is carbon-12. So 99% of carbon, maybe even more, is going to be carbon-12. And then there's a little bit of carbon-13 and a little bit of carbon-14 out there. And it's very insightful. So you can do that for a lot of your elements. I can look at nitrogen. Nitrogen has isotopes. Most of your elements do have isotopes. And it has a mass of 14.007. That tells me that even though there might be isotopes, nitrogen 14 is the most common one. That's the one we're most likely to encounter. There are other ways to symbolize our isotopes. We can symbolize them in elemental form. So just looking this over so we could start practicing it, your mass number is always going to be in the upper left-hand corner. I know as a student I struggled. I'm like 4 and 2, which one is the mass number? The mass number is always the larger of the two. It should be, right? Because the mass consists of protons plus neutrons. So it's just going to be the largest value that you're going to see on your elemental symbol. Then the smaller value on the left-hand side is going to be your atomic number, which, again, just to really emphasize that point, it's also equal to the number of protons. So if they didn't tell me that this was helium, all they told me was 2, I could go to my periodic table and find number 2. Oh, number 2 is helium. So just based off of the number of protons, you can identify the element. Charge. So we've been dealing with a lot of neutral species, and if there's nothing written there, so say you just saw something like this, 4, 2, helium, and there was absolutely nothing written here. That means that the neutral charge is understood. And it's understood to be 0. I want to point that out because that's a tiny bit different from what we see down in the lower right-hand corner. Here, this tells us how many atoms of a particular element we're dealing with. So at this point in the course, we're going to get there by the end of the week, but at this point, we've just seen monoatomic and diatomic elements. So hydrogen is diatomic, and so we're going to put a 2 down there. So we have 2 atoms of hydrogen. Helium, on the other hand, is monoatomic, and so there's a 1 here, but nobody writes the 1. You just assume that there's a 1 there. So more of these tables are a little bit different than the tables you saw in the previous lecture, because when we're given isotope symbols, we do not want to use the periodic table for mass information. Let's jump in, and hopefully my advice here, my warning here, will start making some sense. So by all means, you can look up an atomic number on the periodic table. The number of protons associated with a particular element is constant. That doesn't change. So, but I don't even need to here because I know that my larger value is my mass number, and my smaller number represents the atomic number or the number of protons. So I'm going to do 38 here, and I'm going to do protons as well while I'm at it. And since I was told that this is a neutral isotope, I also know that the number of protons, the number of positive particles in the nucleus, will equal the number of electrons, the number of negative particles in that cloud around the nucleus. So I'll write a 38 here. Mass now is going to be the larger of the two values, which is an 84. And you might remember from the previous table how to calculate the number of neutrons. You're going to do your mass number minus your number of protons. Alrighty, I promised to tell you why you shouldn't use the periodic table. So here's our first example, strontium. According to this table, we're looking at an isotope with a mass of 84. If you look up strontium on the periodic table, it has a mass of 87.6. So definitely not a match. And we would have been incorrect if we just grabbed the mass from the periodic table. You're not always incorrect, but again, it's just good practice not to reference the masses on the periodic table when you're doing the isotope tables. Let's do a couple more examples. So here we have 47 protons. That information is crucial to help me identify which element we're talking about. So I'm going to look for number 47 on the periodic table. Happens to be silver, ignoring that number. So I'll do Ag here. I'm going to put a 47 in the lower left-hand corner. That's also going to tell me the atomic number and the number of electrons. My mass number is 109, so I could put that on top. And then I need to do 109 minus 47 to get the number of neutrons here. We're looking at 62 neutrons. Let's do a couple more. Number 9, atomic number 9, because it's got 9 protons, 9 electrons. That's going to be fluorine. So I'll put a big F here and put the 9 down there. The mass is equal to protons plus neutrons. So this particular isotope of fluorine has a mass of 18. Last one, we have carbon. Carbon has an atomic number of 6 protons, and it's neutral, so it has 6 electrons. The mass is going to be the sum of the protons plus the neutrons. They gave us the mass number, so we'll do 13 minus 6, which gives us 7. So I can work backwards. 7 plus 6 equals 13. And again, if you looked at the periodic table, you would have put a mass of 12 and you would have been wrong. So don't use that periodic table. How do they get the information about mass that you see on your periodic table? And why does the mass on one periodic table differ slightly from the masses on other periodic tables? Well, it comes down to the calculation. Scientists gather a bunch of information about the percent abundance of particular isotopes in nature. So this tells us that carbon-12 makes up approximately 98.93% of all of the carbon out there. And carbon-13, that's the radioactive version that, if you know about when they date older manuscripts and stuff, and they say, well, we used carbon dating. That's based off of carbon-13. And it's much less common. That's only 1.07% based off of this data set. So once you have the information about the different percentages, how common it is, you can use that along with the masses to calculate what's known as a weighted average. And that's how they get the numbers on the periodic table, and that's what we're going to learn how to do. Now, why the numbers change from one periodic table to the next is because we're constantly updating this information. And there's all kinds of extraction of elements from the ground or discovery of new deposits. And so after those new samples are analyzed, the percent abundances may change slightly. And so then that impacts new periodic tables as they're being published. All right, so how does this work? You're not going to do this in percents, right? You never really do anything in percents. So the first step is to take your percents and turn them into decimals. by dividing by 100. So I'm going to do 0.9893, and I'm going to do, be careful here with the 1.07%. You need to move the decimal place over 2 spaces, or just divide by 100 in your calculator. But we're going to 0.0107. So after you've converted your percent abundances to decimals, your atomic mass is equal to the mass of the isotope. So we'll do 12.000 AMU times 0.9893 plus the next one, 13.003 AMU times its decimal abundance, so 0.0107. I'm going to do this problem in 2 steps so that we can analyze the Sig Figs. So first I'm going to do 12.000 times the 0.9893, and I'm going to write down the whole number. So I'm getting 11.8716 AMU. I'm not rounding yet, but we are going to talk about Sig Figs. When I multiply the 13.003 times 0.0107 over here, I get 0.1391321, and it has units of AMU. So this number has 5 Sig Figs. Those zeros count because they're to the right of the decimal point and to the right of a non-zero digit. Over here I have 4 Sig Figs. I'm multiplying, so I'm going to do 1, 2, 3, 4. So the last significant digit in that first number is the 7. 5 here, 1, 2, 3, just 3 here. So the last significant digit in this number is the 9. Let's put little marks above my last Sig Fig, my smallest value, smallest digit that's significant. So now's adding. I'm going to add up these 2 numbers, not really a huge deal, just throw them in the calculator. No rounding yet. And I get 12.0107321 AMU. This went 2 decimal places. This went 3 decimal places. So I can only go 2 decimal places on my answer. So I'm going to stop it at the 1. So my final answer, I'm going to say that carbon has an atomic mass of 12.01 AMU. I don't know about you, but it wasn't too bad when we had the information organized in tabular form, in a table. So I think that's the approach that I'm going to take with number 9. I'm going to set up a table that looks very similar to what we saw in number 8. So first we have the isotope, and then we have percent abundance, and I'm going to leave myself some space for the decimal form of the percent abundance, and then I'm going to put mass as my last column. So an element has 2 naturally occurring isotopes. Isotope 1, okay, there's no name of it, it's just isotope 1, has a mass of 120.9038 AMU and a relative abundance of 57.4%. Isotope 2 has a mass of 122.9042, and find the atomic mass of this element and identify it. So first things first, we don't get the second abundance? Not such a huge problem because all of the percent abundances have to add up to 100% by definition, right? A percent means out of 100. So to find this percent abundance here, I'm going to do 100% minus 57.4%. And that gives me 42.6%. So I know isotope 2 has a percent abundance of 42.6%. I'll just divide them by 100 or just move the decimal place to the left 2 spaces. All right, so now I have my percent abundances in decimal form, and now I can set up the atomic mass calculation. So I'm going to do the mass of isotope 1 times the percent abundance in decimal form plus the mass of isotope 2 times its percent abundance. And there's just 2. Sometimes there's 3, 4 isotopes, and you just roll with it, right? So on the first one, I'm going to multiply those 2 numbers. I get my answer. And I do want to do some analysis of the Sig Figs here. So 7 Sig Figs and 3 Sig Figs. So I'll just put a little mark there. Over here I get 52.3571892. Again, just 3 Sig Figs. And both of these still have units of AMU. I'm going to add them together. And I get a mass of 121.7559. Okay. We know I could write much more of the number, but I'm not even going to because we have to stop at the 10th place with this number and the 10th place at that number. We just have one decimal place in both of our numbers. So 121.75, I'm going to round up and I'm going to report my final answer as 121.8 AMU. Now they asked us to identify the isotope. So if we grab our periodic table, now we can use the periodic table because we're looking up a weighted or average atomic mass. 121.76. That's got to be it. We're looking at isotopes of antimony or Sb. Number 10. Calculate the average atomic mass of sulfur if 95% of all sulfur atoms have a mass of 31.972 AMU, 0.76% have a mass of 32.971 AMU, and 4.22% have a mass of 33.967 AMU. Isotopes. So the mass is very specific, but this 31.972 is super close to 32. So this is going to be sulfur 32. In a similar fashion, I'm going to round that number up to 33, and this is going to be sulfur 34. And my atomic mass is going to be equal to the mass times the percent abundance in decimal form. So I'm just moving that decimal point over 2 spots as I'm writing it. You could do it ahead of time as well if you want to take that extra step. It's totally up to you. Ooh, this one, right? Definitely take your time on that one. You got to move it over 2 spots. So it's going to be 0.0076. And I'm going to put the last one underneath. Move it over 2 spots. So we're looking at 0.0422. So in terms of Sig Figs, we have 5 Sig Figs and 4 Sig Figs. So we'll maintain 4 Sig Figs with the first value, 5 Sig Figs and 2 Sig Figs, and then 5 Sig Figs and 3 Sig Figs. All of these values have their last significant digit or their smallest significant digit in the hundreds place. So I can maintain my mass to the hundreds place or 2 decimal places. This 7 though is a little bit big, so I'm going to report my answer as 32.06 AMU. Is there any way to check our work? Well, sulfur 32 is 95% of all of the isotopes out there. So therefore, our final answer should be close to 32. And it is.